reduction in the amplitude of wave 1 of the auditory brainstem response for these animals, and that tells us about the response of the auditory nerve. So there's a big reduction, permanent reduction in wave 1 amplitude for these higher level stimuli, but at the lower levels there's very little change in wave 1 amplitude. And the reason for that seems to be that this particular type of trauma affects a particular group of auditory nerve fibers. So they're damaging the synapses between the inner hair cells and the so-called low spontaneous rate auditory nerve fibers. And these fibers are the ones that are responsible for coding information at these higher levels. So when Kajal and Liebman did histology, as we've just seen, there was a large reduction in the synapses, the connections between inner hair cells and auditory nerve fibers, and then over a period of about a year, the nerve fiber will atrophy. And so then if you look in the spiral ganglion, there we go, you can see these holes in where the cell bodies used to be in the spiral ganglion. So about a year after the trauma, eventually the nerve fibers have atrophied all the way up to spiral ganglion. You get about 50% ganglion cell loss. So here we have a noise trauma that's produced in the mice. We typically call a temporary threshold shift. Threshold sensitivity recovered to normal. But in the affected frequency regions, they end up losing half of their auditory nerve fibers. So it's a significant dysfunction. And so this is just my little sketch of what's going on here. So here's an inner hair cell, and you can see it's connected by a number of auditory nerve fibers. Noise exposure, and the mechanism for this is thought to be mainly glutamate excitotoxicity, so it's too much release of the neurotransmitter at the synapse, causing swelling in the terminals, and the terminals break away from the synapse. And then in the case of mice, over a period of time, a year it takes in mice for these nerve fibers to generate the spiral ganglion. In humans it's thought to take quite a bit longer, maybe 10 years, for the synaptopathy to the loss of the cell body of the nerve fiber. Okay, so just to summarise where we are on cognitive synaptopathy, in rodent models this has been demonstrated now in mice, in guinea pigs, and also more recently in chinchilla. But there hasn't been a model for this, or at least it hasn't been published yet, work done on primates. So in rodent models, noise exposure can cause substantial loss of the connections, synapses between inner hair cells and these low spontaneous rate nerve fibers which code information at high levels. And these are the ones we actually need for most of our everyday hearing. These are the ones that we're using mainly when we're listening to conversations, for example. This disorder, it's been termed, the technical term is cognitive synaptopathy, but it's also been called hidden hearing loss by Roland Chater and David Alpine, because it's not thought to be detectable using pure tone audiometry. This is a supposition because you're not affecting the responses at low levels. So a crucial question, of course, and a lot of labs around the world are investigating this at the moment. Is noise-induced cognitive synaptopathy an important cause of hearing impairment for human listeners? So I'm just going to tell you a little bit about one study that has been done looking at the relationship between noise exposure and the auditory brainstem response. So the auditory brainstem response, as I've just mentioned, you present a brief stimulus, you can use a tone burst or a click, and you get a number of peaks at various time intervals. So wave 1 comes about 1 or 2 milliseconds after the stimulus, and then wave 5 maybe 5 or 6 milliseconds later. And each of these peaks represents the electrical response or population of neurons in the auditory system. And wave 1 reflects the response of the distal portion of the auditory nerve, and wave 5 the response of the inferior colliculus in the rostral brainstem, so quite a fair way further up the auditory pathway. So this is a study that was published last year by Stamper and Johnson, and they had a group of young participants, and they estimated their noise exposure using the questionnaire, but they only estimated noise exposure over the previous year. Okay? So it was a kind of a proxy measure, if you like, of their total noise exposure over the lifetime, which, because this is a permanent deficit, we think is the most important thing. But anyway, they showed quite a nice, I mean, they didn't have a huge number of participants, but they showed quite a nice relationship. There's a lot of variability in wave one, as you probably know if you've ever studied this, but they showed quite a nice, significant relationship between noise exposure and wave one amplitude. And this seems to, these are high-level clicks, by the way. And we've got here a 90 dB NHL click, which I think is about 120 dB, peak equivalent SPL, so it's incredibly loud. I'd be scared about presenting this to my participants. So they showed this reduction in wave one amplitude at high levels, as you might expect, related to noise exposure. So this looks at face value to be to mirror what's happening in the rodent studies, and suggests that a similar kind of deficit is manifest in humans who are exposed to noise. However, one of the potential confounds of this study was they didn't separate out their results by sex, and we know that males are both more likely to expose themselves to high noise levels, and possibly mainly because of head size, they have lower ABR amplitudes. And indeed, when they followed this up with the letter, because people asked them about this, and what they found, this was indeed the case, the males in their sample, so these are results just for the very highest click level, these are the ones that were presented in this follow-up. And they found that the males indeed had a high noise exposure, but they also had the lower amplitudes. And when they analysed it up separately for sex, they found they still had a significant result for females, as you'd expect, but the males, if anything, went in the other direction, although it was non-significant. So there's still a little bit of confusion about what these results actually mean. Now, Stanford and Johnson matched their audiograms of their participants across noise exposures up to 8 kilohertz. But it's not clear in their reanalysis whether this was done separately. Well, they didn't present any evidence that it was done separately for males and females. So there's still a little bit of uncertainty about this. So there's evidence, that sort of suggests that there might be something going on, but the picture is certainly not conclusive. So this brings us on to our study, which we started a couple of years ago in Manchester. And our aims were to determine if cochlear synaptopathy is prevalent in young, audiometrically normal adults as a consequence of noise exposure, and also to have a little bit of an investigation to see what the impact of cochlear synaptopathy might be on real-world listening ability. And so in this talk, I'll just show you some of our results for speech and noise. We have run a huge battery of tests on these people, which we're going to be presenting over the next year or so as we do the analyses. So these are our participants, and they're relatively young, so we went from 18 to 36 years of age, and we used a questionnaire that was developed by Mark Buckman and colleagues that estimates lifetime noise exposure. And so, as you might expect, our noise exposure measure here, our noise exposure measure here varies with age. So as people get older, they accumulate more noises. The total energy of noise exposure increases. Now, the noise exposure scale we're using here is a logarithmic scale. And each unit on this scale represents a factor of 10 in terms of the total energy of exposure. So from the lowest exposed to the highest exposed, we're covering a range of several hundred in terms of the total energy of exposure. So we have quite a wide range. We have from people who don't go out to nightclubs, don't listen over personal music players, and have very low exposures, to people who actually work in nightclubs without hearing protection every day of the week. So that gives you an idea of the range of noise exposures we have in this sample. Now, we also broke out, as well as having, so we have 130 participants in this sample, so it's a bigger study than the Stanford and Johnson study. And just for illustrative purposes, I'm also showing you here the results for the 25% of the participants with the lowest noise exposures and the 25% with the highest noise exposures. And this is just another way of visualizing the data. And what you can see from the audiograms here is that we actually match the audiograms very well up to about 8 kilohertz. But at 16 kilohertz, there was an effect of noise exposure. So at this very, very high frequencies, we are seeing an effect of noise exposure. So even though people might have completely normal audiograms in low frequency region, they might show this high frequency loss. And that's kind of interesting for interpreting the ABR results, because we know that the auditory brainstem response, particularly wave 1 the auditory brainstem response, is very sensitive to basal or high frequency generators. So we have to be very careful about not confounding a measure of synaptopathy with one where we're just sort of measuring the sensitivity, the high frequency sensitivity. So these are the mean ABR waveforms for the low exposure and the high exposure groups. And this is in response to our highest level clip, which wasn't quite as high as the Stanford-Johnson clip, it was 100 dB, the equivalent SPL. And what you can see, so here is wave 1 of the ABR, which, as I've said, is a measure of auditory nerve function. And you can see that just from this, that there's very little difference between the low noise exposure and the high noise exposure groups for our primary measure, wave 1. And this also is true for the other waves in the ABR. In fact, these waves are very, very closely matched. So just from looking at this, you can see we're not finding, at least in our sample, very good evidence for this kind of synaptopathy that was very clear in the animal models. And if you have a look at the correlations here, you can see that across the different noise exposures, there's no relationship at all between noise exposure and wave 1 amplitude here. And the R-square value is 0.00, which I can describe confidently as a null result. So we can also have a look at the peak to trough amplitude at the two levels. The reason we use these two levels is so the reason we use these two levels because you expect the effects of noise exposure, according to this, the animal model of synaptopathy, to affect the highest level, these high level clips, but not to affect the lower level so much. And so we're going to use that as a within the participant comparison. But as you can see, at neither level did we see any effect of noise exposure on wave 1 amplitude. Okay, so the speech and noise tests we tried with these participants. We used two different types of tests. We had the coordinate response measure, where you're listening basically to a speaker in the presence of other speakers. We had two competing speakers. You listen for your call signs. So you might hear, ready, Baron, go to green 3 now. Okay? So if you hear the word Baron, as opposed to other call signs like sort of Charlie or whatever, then you have to then respond on the computer that you, with the colour and the number. So you go green and 3. Okay. Now we use two different types of interfering stimulus, one of which in which the speakers were positioned straight ahead of the listener using virtual head-related impulse responses to create a virtual auditory space. So there's one case where they were co-located with the target, and the other one where they were to the side, so they're spatially separated. So it's testing people's ability to separate out speakers with interference. So this is a kind of more kind of real-world thing if you're in an environment where you had several people speaking at once and you're trying to listen to one conversation. We also used a task, a simple task called the digit triplet task, which is where you hear 3 digits spoken in background noise. You might hear sort of 5, 6, 1. You just have to indicate by pressing on the keypad what those numbers were, and then you can change the level of the background noise to find the threshold. We presented the stimuli for the digit triplet task, presented dialectically at 80 dB SPL. The way these are plotted, good performance is going down. So we just because we had so many different tests, we didn't want to confuse ourselves. So we always have it so that good performance is good performance is going up. I'm confusing myself already. Good performance is going up, so we expect the effect of synaptopathy as you increase noise exposure. We expect the line to go from the top left to the bottom right. But you don't really need to know that, because all you need to know from these is that, again, we have a very, very strong null effect. These correlations are completely flat, and there's no relationship between noise exposure. Remember, this is noise exposure at quite a long range. For these young, audiometrically normal listeners, there's no effect of noise exposure on their speech and noise performance. Okay, so the summary of this study is that none of our main measures, and we tried lots of other things as well, showed a significant relation with noise exposure despite the wide range of exposures and the high statistical power. So there are three possible explanations, we think, for these results. One is that hidden hearing loss, this type of cochlear synaptopathy, is not very prevalent in young, normally hearing adults. Or even listeners with comparatively low levels of noise exposure have this disorder. I mean, that's quite possible, right? Because people in industrial society are routinely exposed to quite high noise levels, and that there's no additional consequence of higher levels of noise exposure that they're measuring. So these can be sort of summarised in that no one has hidden hearing loss, or that everybody has it. Okay. There's another possibility, of course, which is that our measures that we use are insensitive to this cochlear synaptopathy. And although wave 1 seems to be reflect cochlear synaptopathy in the rodent models, it's possible that it's not sensitive to cochlear synaptopathy in humans. And in fact, there's some evidence that wave 1 amplitude might not tell us that much about the function of low spontaneous rate fibers. I don't have time to discuss that today. One of the things we did find, and it has been reported before, is that this is kind of an interesting effect, is that there was a, although the audiograms are very, very closely matched up to 8 kHz, at 16 kHz, there's quite a difference between the noise exposed and the non-noise exposed groups. And it's worth remarking that this might be a good, useful early marker of the risk of future hearing loss within the lower frequency range. For example, if this might be useful in sort of health surveillance, if someone's working in a noisy environment, you want to find out whether they're in danger of losing their hearing at a later date. Okay, so that part of the story is looking at the noise exposure and relating it to this physiological measure and to speech perception and noise. But it's also been suggested that this type of disorder, cochlear synaptopathy, hidden hearing loss, is a cause of tinnitus, particularly in individuals with audiometrically normal hearing. We know that some people who have normal audiograms still experience tinnitus. And so this is a study which coined the phrase hidden hearing loss by Roland Shater and David McAlpine. And what they found, they had young, normally hearing listeners, they matched the audiograms fairly well, up to about 12 kilohertz. And they found that the listeners with tinnitus had a reduction in ABR wave 1 amplitude, particularly at the highest level they tested, 100 dB peak equivalent SPL. Now what's interesting about this study is that they also had a look at wave 5 amplitude, and they found that wave 5 amplitude was relatively unaffected by the tinnitus. So there's no significant difference, you see it in the right-hand panel here, between the tinnitus group and the control group of wave 5. So that's a response in the inferior colliculus and the rostral brainstem here. Anyway, so the inferior colliculus in the rostral brainstem, there's no difference in tinnitus and non-tinnitus listeners, but in wave 1, which reflects auditory nerve function, there seems to be a reduction in the response of the auditory nerve for the people with tinnitus compared to those without tinnitus. So their explanation is that what might be happening in tinnitus, at least in this particular type of tinnitus, is that for the normal auditory system, when you have a complete set of connections, complete set of nerve fibers innervating each inner hair cell, you're going to get a certain response in the auditory nerve, and then there's going to be various processing that goes on the brainstem until you get to degenerators of wave 5 of the auditory brainstem response in the rostral brainstem in the inferior colliculus. And you can model this, this processing very crudely as some sort of gain mechanism, some sort of amplifier control that determines a relation between the response in the auditory nerve to the response at this higher level in the auditory pathway. Now, if you have a reduction in the amplitude of wave 1, a reduction in the response from the auditory nerve, then the system will compensate for that by essentially turning up the central gain, just like turning up the volume control on your amplifier. And this might restore wave 5. This is kind of a homeostatic mechanism to make sure that the response in the high-level auditory system is not affected by this peripheral dysfunction. However, and this is their sort of account for tinnitus, if of course we turn up the volume on your hi-fi or radio, you're going to amplify any background noise. In this case, it might be background neural noise. And so that might be what gives rise to tinnitus. I think you're going to sort of amplify the response, the neural response in the brainstem, and this is amplifying the spontaneous activity of neural noise. So this was a really nice study that seemed to provide an explanation for why people with normal audiograms might get tinnitus. One of the things that they didn't do in this study, however, was measure the noise exposure for these group of participants. And as far as we're aware, some of you might have some information on this, that no one had actually done, until the study I'm about to tell you, there was actually measured noise exposure for people with tinnitus with normal audiograms to see if that might be the causal factor. We might expect it would be, but this hasn't been done before. So in this particular study, this is Hannah Guess, my PhD student, who's been conducting. We wanted to determine, first of all, if tinnitus with normal audiogram is related to noise exposure history, or maybe there's some other cause. And we wanted to try and see if we could replicate the Shater-McAlpine result to see whether tinnitus with normal audiogram is associated with cochlear synaptopathy, as indicated by reduction in wave 1 of the ABR. And also to investigate further this central gain hypothesis. So we had 18 participants in each group. They were fairly young, with a mean age of about 25 years, and they were roughly evenly distributed between males and females. Now we individually matched our participants for age and sex. Okay, so they were sort of pair matched, and we had one tinnitus, one control at each age and sex. And they were group matched for pure tone audiometry. And if you have a look at their audiograms, the tinnitus and control groups, you can see we actually did a really good job at matching their audiograms up to 8 kilohertz. They're very, very close. We even did some high frequency audiometry, which you can see on the right here, and even up to 14 kilohertz. The thresholds for the tinnitus and the control groups were very closely matched. So to answer our first question, have a look at noise exposure history. Yes, as you might expect, there is quite a strong relationship between tinnitus and noise exposure history. People with tinnitus, even though they might have normal audiograms, have a history of noise exposure. So we know that noise exposure, well, the implication here is that noise exposure is causing the tinnitus in some respect. And obviously, the possibility is that this is due to this cochlear synaptopathy I've heard about. So it's related to noise exposure in some respect. However, we're sort of the kings and queens of the null results at the moment, we found no difference at all in ABR amplitudes between the control group and the tinnitus. This is a similar plot we've shown before. These are the averaged ABRs across the two groups. And you can see in particular for wave 1, which is the peak on the left there, there's no difference between the tinnitus and the control groups for our higher level clicks. So we didn't replicate the Shater-McAlpine study. We're fairly confident in our results. Hannah did a really good job at measuring these ABRs. You can see these are standard errors here. We have really good reliability in our results, both for wave 1 and for wave 5. So we can say with a good degree of confidence that for our tinnitus groups did not seem to have any neural function, at least as measured using wave 1 of the ABR. So if we compare these are our results here with standard errors, and these are the results from the Shater and McAlpine study. You can see there's a clear, distinct difference in the pattern of results here. So of course we have to try and understand why this should be. One of the reasons that we don't think is that important, Shater-McAlpine used slightly wider bandwidth headphones. They might have been stimulating quite a slightly higher frequency region. There isn't that much difference between the headphones they used, TGH49s versus our insert ER3As, but maybe that had some kind of effect. Although Shater-McAlpine did a pretty good job at matching their already mentioned thresholds, there was still a little bit of a hearing loss at 12 kilohertz. The tinnitus group were about 3.5 dB had a 3.5 dB worse hearing than the control. So that doesn't sound like very much, but with a 10 dB reduction in the click stimulus, you can almost halve ABR wave 1 amplitude. So even 3.5 dB reduction here, if wave 1 is being produced by these basal generators, that might be enough to count the results. And it's possible also they had some hearing loss at higher frequencies that was affecting their ABRs. But perhaps our kind of favourite explanation for why there's a difference between these studies, is something that we're following up at the moment, is that the mean age in the Shape McAlpine study was 36, and for the tinnitus group and 33 for the control group, but our mean age across both groups was 25. So it's possible that cochlear synaptopathy might be one of the causes of tinnitus in normal audiogram, but perhaps it only becomes manifest as you get older, and perhaps other causes are more dominant in the younger group. And this is something we're exploring by having a look at a higher age range using our particular design methodology. So, to summarise this study, tinnitus of normal audiogram is associated with a history of high noise exposure. There's no evidence, though, from our ABR data that tinnitus of normal audiogram is associated with this kind of synaptopathy or loss of low spontaneous rate auditory nerve fibres or an increase in the central gain. So overall, just to summarise where we are in the study, and I would say that this is arguably the hottest topic in hearing science at the moment. Loads of people are sort of investigating this from lots of different angles using different measures. And so it's kind of an exciting time as these results come out and we try and get a clearer picture. But it's very clear from rodent models that noise exposure can result in this type of deficit, this cochlear synaptopathy, without affecting sensitivity to soft sounds, and this is being called hidden hearing loss. The results I've shown you suggest that noise-induced cochlear synaptopathy is either not very prevalent in young adults, or maybe is not being revealed by ABR wave 1 or speech and noise tests or any of the other things actually we tried on them. So it's possible that our measures are not sensitive to cochlear synaptopathy. But the way things look at the moment, at least for these young, normally hearing adults, I'd say that there isn't very good evidence that cochlear synaptopathy is a major concern. However, that doesn't mean that cochlear synaptopathy is not going to be something that we should worry about for human listeners. Now, one of the things about the mouse study, and studies where you can actually control the noise levels that you're presenting to the participants, is you can get the noise level just right so that you can cause this temporary threshold shift and you can cause this cochlear synaptopathy without producing a permanent threshold shift. And of course we can't do the experiments ethically on human listeners, we just have to take their self-report noise exposure. And it could be for humans that there's actually a very narrow window of levels, if you like, which can cause this synaptopathy without causing a permanent threshold shift. And that's kind of where we're thinking this is going at the moment. So that it could well be that by selecting just young listeners with excellent hearing, we're effectively excluding those who have any kind of synaptopathy, but perhaps picking listeners who might be resistant to the effects of noise exposure, perhaps they can take on antioxidants or something. But anyway, what I'm saying here is that our results only really apply to these young, normally hearing adults, young adults with good hearing. It remains a distinct possibility that listeners with some sort of mild hearing loss also have cochlear synaptopathy. This can be very interesting. This is something we're trying to do at the moment, to disentangle these different effects of hair cell loss and the neural damage you get through that synaptopathy. If we can sort of pull these apart, that might have implications for how we treat people with hearing loss. Okay, so that's the end of my story. Just I won't read out the names, but these are all the people who are working on these outcomes.